In this video, we're going to look at some properties of infinite series. If summation n goes from 1 to infinity, is equal to a, that means this infinite series converges and has the sum a. And summation n goes from 1 to infinity bn is equal to b, that means this infinite series also converges and has the sum b. And if both of these are convergent series with the given sums a and b, then summation n goes from 1 to infinity an plus bn converges to the sum a plus b. And similarly, summation n goes from 1 to infinity an minus bn converges to the sum a minus b. Part C. If c is a real number and summation n goes from 1 to infinity c times an, this will converge to the sum c times a. The reason for this is that c is a constant, passes through the summation, so we get c times summation n goes from 1 to infinity, and we get c times a. Now let's look at some examples where we apply this theorem. Find the sum of the following series if the series converges. So we have summation n goes from 1 to infinity, 1 plus 2 to the n divided by 4 to the n. Part B, summation n goes from 1 to infinity, e over pi to the n plus pi over e to the power of n. Let's look at part A first. We have summation n goes from 1 to infinity, divide through the fraction, so we get 1 over 4 to the n, plus 2 over 4 to the power of n. Now let's split up this sum, so we get summation n equals 1 to infinity, 1 over 4 to the n, plus summation n goes from 1 to infinity, 1 over 2 to the power of n. Now we have a sum of two convergent geometric series because both of these have pattern summation r to the n, and this one is also summation r to the n. They're both geometric. Now if you look at the first series, summation n goes from 1 to infinity, 1 quarter to the power of n, the common ratio is 1 quarter, is less than 1, and therefore the series converges. The first series converges. And for the second series, n goes from 1 to infinity, 1/2 to the n, we have r is equal to 1/2, and 1/2 is less than 1, so the second series also is a convergent geometric series and converges. Both of these series are convergent geometric series. They both converge, and we can apply the sum s is equal to a divided by 1 minus r, because in both cases the common ratio, the magnitude of the common ratio is less than 1. We have r equals 1 quarter, that's less than 1, and r equals 1/2, that's less than 1. So basically we apply this formula and add up the two sums. All right, so what we have is summation n goes from 1 to infinity, 1 plus 2 to the n, divided by 4 to the n. We split up the sums, and we wrote this as a sum of two geometric series. N equals 1 to infinity, 1 quarter to the n, plus summation n goes from 1 to infinity, 1/2 to the n. Now apply the sum formula for each geometric series. For the first one, plug n equals 1 to get the a, the starting term. Plugging the index n equals 1, we get 1 quarter to the 1. That means a is equal to 1 quarter. And divided by 1 minus, the common ratio is, of course, 1 quarter. The common ratio is 1 quarter. For the second geometric series, we have the first term, plug n equals 1, we get 1/2 to the power of 1. So a is equal to 1/2. That goes in the numerator. Divided by 1 minus r, the common ratio is 1/2. Now let's show that, let's go over that. So for summation, n goes from 1 to infinity, 1 over 4 to the power of n, a is equal to 1 quarter because we plug n equals 1. So always plug your first index, plug n equals 1. In this case, it starts at n equals 1 to get a, to get the first term a. And the common ratio is, of course, 1 quarter. All right, so summation n goes from 1 to infinity, 1 plus 2 to the n, divided by 4 to the n. We split this up as the sum of two geometric series. So we get 1 quarter, divided by 1 minus 1 quarter is equal to 3 quarters, plus 1/2 divided by 1 minus 1/2 is 1/2. The 4's cancel out, so we get 1/3. And 1/2 cancels with 1/2. 1/3 plus 1. That's 1/3 plus 3/3. That's 4/3. So the given series, which is a sum of two convergent geometric series, converges with a sum. Sum is equal to 4/3. So we can write n equals 1 to infinity. This infinite series converges and has the sum. The sum of this infinite series is 4/3. All right, let's look at part B. So for part B, we have summation n goes from 1 to infinity, e over pi to the power of n, plus pi over e to the power of n. Let's split up the sum and evaluate each series separately. So what we have is summation n equals 1 to infinity, pi over e to the power of n, plus e over pi to the power of n. This is equal to, let's split up the summations, n equals 1 to infinity. I'll write the second one first. The order doesn't matter because we're just adding e over pi to the power of n, plus summation n equals 1 to infinity, pi over e to the power of n. Now, both of these series have the pattern summation n equals 1 to infinity, r to the n, and hence are geometric series with common ratio r. The first series has r equals e over pi, so that's the first series, the common ratio is e over pi, and since e is approximately 2.718, is less than pi, which is approximately 3.14, so the ratio will be less than 1. R is less than 1 and converges. However, the second series has r equal to pi over e, and pi is approximately 3.14 and e is approximately 2.718. The ratio pi over e will be bigger than 1, and hence the second geometric series diverges. And if one of them diverges, the whole thing diverges. So basically the entire series, summation n equals 1 to infinity, e over pi to the power of n plus pi over e to the power of n diverges. So let's go over some theory. If the series summation an converges and summation bn is a divergent series, then summation n goes from 1 to infinity, an plus bn diverges. So we need both of them to converge. Both series, summation an and summation bn, must be convergent. They must converge to a sum in order for the entire series, summation the n goes from 1 to infinity, an plus bn to converge. In this case, this was the bn here. This was the bn that was diverging because pi over e, the common ratio pi over e, r equals pi over e, is larger than 1, and hence it diverges. So that's the reason for this series diverging. So the entire series will diverge. All right, thanks.